Hello everybody. In this video what we're going to be looking at is the actual design of the sensor. So this part wasn't covered very well in the presentation or the paper, so I thought this would be a good opportunity to go over the design more, since that was one of the highly requested things on the poll of what you guys wanted, more discussion about. So let's go ahead and walk into it really quick. So just to catch you up, there's a video before this that kind of primes you on how microgeometry influences how light interacts with the surface. But just a quick catch up, this sensor is going to be based off the aluminum silver dollar pigment that we use for this sensor, because this type of pigment has this nice property that as light comes in and hits the surface, it tends to reflect in a direction, like a desired direction, but there is a little bit of variance where some kind of, irregularities on the surface, like, the staircase or something that's not, it's kind of sticking up instead of being parallel with other things. Those kind of imperfections will, cause some rays to travel, a little bit of a different direction than most of the rays are traveling, but just slightly. And so you can see here, most of them travel in the normal direction that you would expect if you had a mirror surface, and then some of these rays are just going off into some other directions. And so the reason that we're going to use this type of pigment instead of the other pigment that we used in the previous sensor is because we really want our light to travel in directions that we specify. So this is the basic kind of setup of the sensor. We have, a hollow cavity here, with air, and here, this kind of white area that's outlined is a plastic shell that's clear, and on that plastic shell is the sensing surface with the silicone and the, painted surface with the silver dollar aluminum pigment. And then, of course, we're going to be observing this with the camera, and let's kind of walk through how this actually plays out. So we're going to look at only this LED here, and we're going to emit a few rays and just kind of, follow its path. So the important principle behind this design is that we have this sensing surface that has that silver dollar coating, so it will reflect in the direction we want. And because we're actually working with a clear plastic shell that's pretty thin, we can actually use the principles of total internal reflection to actually keep the light in. So what does that mean? So if we look at this right here, when it hits the plastic surface, if its angle that hits the surface or the plastic air boundary is less than some angle, what will happen is it won't actually escape out of the plastic shell, but will be reflected back towards the sensing surface. So here's another, situation where the light comes in, it hits our sensing surface, it gets deflected into some or reflected into some direction, and its angle is actually greater than the angle of TRI. And so it just bounces out of the surface and just, bounces out in this air region and then goes wherever. I wouldn't know what the trajectory of that would be. And then finally, we have some nice rays that come in, hit the surface, go out from the angle, hit the surface again, hit the surface, hit this, plastic air boundary, bounce off, and then stay within the sensor until it reaches the end, where it's absorbed by a filter. And since we have enough lights coming in parallel like this, what will happen is some rays will have rays that are, very close or hug the surface of the sensor. And then, so all along the sensor, you're going to have these, almost parallel at that infinitesimal spot with the actual sensing surface. So now, when you actually go and press an object into the soft surface, what will happen is, a ray its track will get interrupted, hit that part of the sensor, and then bounce out because it's greater than the TRI angle, and it hit our camera. And then from the previous video, if you guys watched it, we can use that, intensity of light at this pixel to estimate the actual gradient at that location. And then we have some rays that kind of bounce around, and they go above the actual deformation of the sensor. And so because that happens, it might be the scenario where the area here will actually have some rays hitting it. And so there was a question earlier in the Slack asking, will the sensor actually be able to handle multiple contacts? And, in the actual sensor design, half of this is the rigid part, and then half of this is the rubber part. So it might be the case where, some of the light that stays contained within the rigid part only escapes at some point and then actually comes into the silicone and fills in these areas behind a point of deformation. So yeah, it might be, even though it hasn't been thoroughly tested, it seems like multiple contacts won't be an issue for this sensor. And just kind of to visualize this so you can actually see what an image from the sensor would look like, this is just a screw being pressed down. And so because, there are these, little imperfections in the surface of the paint because of the flakes being in random directions and stuff like that, it's not perfectly black, but what you see instead is it's lightly colored. It's pretty dark still, though. And then when you actually press an object down, what you see is, these bright red spots pop up like you would see here. And then bright blue spots on the other side. And then we also have a third light because you need at least 3 light sources. You want at least one light source coming from the Y direction, and then 2 light sources coming in at an angle like this, 45 degrees, so that you have 2 sources of information for the vertical part of the sensor, and then 2 pieces of information for the horizontal part of the sensor. So let's actually go and see what this actually looks like on the sensor. So this is just the CAD model of the sensor, and I'll just do a quick run through. So here's the mounting plate for the Allegro finger. So we'll hide that really quick if I can figure out which one that is. And so we have 2 PCBs for this sensor. We have a bottom and back PCB. For the bottom PCB, what we do is we have all the green LEDs down here. And then on the back PCB, one side of these LEDs will be the red LEDs, and the other side of these will be the blue LEDs. And so the bottom PCB actually has the input for the actual powering the LEDs. So we power it with 3.3 volts, and then so we have ground and power going into these. And then we have resistors going in because each set of colors needs a different resistor value. Comes in, goes through the resistor, comes to these pins, and then these pins get connected to these guys over here. And they each power one side of the LEDs. And so one of the things that I was showing earlier in the diagram was that there's these parallel lines coming in. So the first thing that we actually did was we wanted to make sure that the lights came in parallel so that there aren't lights coming in at angle and then causing lights to kind of go into the camera and being bright spots just out of the get-go. So we have these blinders here, which are a little bit thicker, and so lights that are actually traveling at angle hit this little area and get absorbed by our piece because it's a black piece. And so only mostly parallel rays come into the sensor. And so there's also one in the back. Let's see. And the actual camera holder. So you can see the slits here. And so we just screw that PCB into this little plate, And then what we do to attach the mounting plate, the actual plastic shell, and the camera holder together is we have our plastic shell here. And we just drive a screw. There's heat set screws into the bottom of the camera plate, as you can see in the inside there. And we just screw it together that way. And there's these little blinders here that also act as a press fit so that we can actually prevent this part from going off or moving back. Since we couldn't really figure out a nice way to actually screw the back part of this into the plastic shell without messing up the optics. And so inside we just have our camera. So the camera that we are using inside is just for this model, the Raspberry Pi V1 camera. And it's a special version of it, which is a spy camera, so it's a bit smaller. And it has I think an M8 lens adapter onto it, so we can actually mount lenses onto that sensor that have a 140-degree field of view, which is nice because we can make this sensor a lot more compact if we have a larger field of view. But it does cause some distortion as you have a larger field of view with the camera. And so with this plastic shell, this is casted. I could talk about this more in the manufacturing part. And then just really quick, we coat that in a 2mm thick silicone layer. So the plastic shell itself is only 1mm thick, but the material we're using is pretty rigid, so there's no deformation if you press down too much on it, at least with the force limits of the hand. And then our silicone's 2mm thick. We're not sure if 2mm is too thin or too thick yet. It's something that we haven't tested yet, but it's something that we would like to look at more into the future. And then let's go ahead and just put the paint on there, and then put the base back. And that's just a quick run through of the design of the sensor. I'll probably post the CAD models soon, so you guys can actually go ahead and interact with it yourself, and then possibly put the PCB designs online as well. So, anyways, that's a quick run through of the design. Let me know if you have any more questions about it, and yeah, thanks again for listening. Bye.